How is energy present in a wheel? The answer to that question is that the wheel has kinetic energy in both its translational and rotational motions. It can have other forms of energy, such as gravitational potential energy if it's high in the air, or nuclear energy if it's made out of uranium, but the energy I have in mind here is kinetic energy, energy of motion. And as I'm about to explain, a spinning wheel on a vehicle carries an especially large amount of kinetic energy. Let's start by looking at the kinetic energy the wheel carries in its translational motion. That is, the kinetic energy that's associated with the wheel's velocity. We can determine that kinetic energy by calculating the amount of work we would have to do on the wheel to bring it from rest to its current velocity. So, we'll start with the wheel at rest. We'll push on it as it begins to pick up speed and move in our direction, and we'll keep pushing until it's moving at the final velocity. And if we know how much work we did, we know how much energy we've invested in that wheel, and therefore we know its kinetic energy. That's the program here. So, rather than doing that calculation completely, which is more complicated than is appropriate for this class, this course, I'm going to explain the most important issues. To do this, make these observations, I need a wheel that can translate without rotating and without friction. So I don't want to have, if I do this, that wheel, yeah, it's translating, but it's also rotating. That just complicates the story. So I can't make this wheel translate without making it rotate. I'll have friction otherwise. So what I'm going to use is this wheel, which is actually a toy puck that rides on a little cushion of air. It's a miniature hovercraft. That cushion of air is created by a battery-powered fan. So when I turn it on, it rides essentially without any important friction. And if I start it from rest and do work on it like this, it carries that work with it as kinetic energy. Nonetheless, it's a wheel. Off it goes, right? I don't have to roll it, though, to get the frictionless effect. So, first observation to make using this interesting little wheel is that the direction of the final velocity I end up with doesn't matter. It takes just as much work to go from rest to moving to your right at a certain speed as it does to go from rest to moving to your left at a certain speed, or toward you at a certain speed. The kinetic energy of this wheel, then, doesn't depend on the direction of its velocity. It depends only on the amount of its velocity, which is speed. So, it's important that kinetic energy doesn't depend on the direction of motion. I've been calling energy the conserved quantity of doing because it's about doing work, not about moving. In the episode on bumper cars, we will encounter the conserved quantity of moving, a physical quantity officially known as momentum. Since momentum is all about moving, going somewhere in a particular direction, it does depend on direction, but energy has no direction and no dependence on the direction of motion. So far we know that the kinetic energy of a wheel depends on its speed. Second important observation is the kinetic energy of a wheel is proportional to its mass. How can I show you that? Well, I have one wheel and a second wheel. Isn't this great? These are two identical wheels. And if it takes 1 unit of work to get that wheel moving to right at a certain speed, how much work do you think it takes to get 2 wheels to go from rest to moving at that speed? It takes twice as much work. Each wheel takes 1 unit of work. Poof, off they go. So, without further ado, it's pretty clear that kinetic energy, the kinetic energy of a wheel or any other object, is proportional to its mass. My third important observation is that the work required to bring a motionless wheel up to its final speed is proportional to that speed squared. That's a rather startling observation. It means that if I double the final speed of the wheel, so say from this to this, twice the speed, I quadruple the kinetic energy, a huge increase in kinetic energy. Now, rather than going into all the details behind that relationship, I'll show you the basic issues behind it. First, let's look at how the wheel's velocity evolves over time. If I exert a steady force on the wheel, so I'm going to push it with a constant force, it accelerates at a constant rate. The acceleration is constant, and so its velocity increases steadily. And basically then, the velocity is proportional to the time over which I've been pushing it. If I double the time over which I push it, I double its velocity. That doubling is not going to work for work. Watch what happens to the energy I invest in that wheel as time goes on. Once again, I'm going to push it with a steady force, and it's going to undergo a steady acceleration. But as it accelerates, it travels faster and faster, so I have to chase it. At first, it's easy to push on it, but then it goes faster and faster. I have to move faster and faster. It's moving faster and faster. The distance it travels with each new portion of time, each new second, is bigger than during the previous second. Well, the work I'm doing is equal to the force I exert times the distance it travels. During the first second, it doesn't travel very far, so I don't do very much work on it. But the second second, it travels farther. The third second, it travels farther still. With each passing second, I'm doing more work on it than the previous second. That means that although its speed and velocity are increasing in proportion to the time over which I push it, the work I'm doing is skyrocketing. It's going faster and faster. I have to chase after this poor wheel and push and push and push longer and longer distances. So that's the origin of this explosion in energy that occurs as the puck's speed and velocity increase. So when all the dust settles and the calculation is done in its full glory, it turns out that the kinetic energy that the wheel has by virtue of its velocity, that is, kinetic energy associated with translational motion alone, that kinetic energy is equal to 1/2 the wheel's mass times the square of its speed. That's the final story, and that's true of any translating object. When I begin to move to your right or to your left, remember, direction doesn't matter. My kinetic energy at any moment is 1/2 my mass times my speed squared. I happen to be a complicated, movable, shape-changeable object. So in my translational motion, you really would concentrate then on my center of mass. And how is my center of mass moving? And take 1/2 of my total mass and multiply it by the square of the speed of my center of mass. Well, this observation that kinetic energy increases in proportion to the square of speed goes a long way to explaining why high speeds are potentially so hazardous. If you compare two identical cars, one traveling 60 miles an hour, which is essentially the same as 100 kilometers an hour, to a second car that's traveling only half that fast, 30 miles an hour or 50 kilometers per hour. They're different by a factor of 2 in speed and velocity, but they're different by a factor of 4 in kinetic energy. That faster moving car carries 4 times as much kinetic energy in its translational motion as the slower moving car. And that explains why collisions that occur at those high speeds are a problem. And modern cars are designed to dissipate that enormous excess in energy, in this case in the form of kinetic energy. They dissipate it both by grinding it up, in part into thermal energy and in part into the deformation and destruction of safety zones in the car, portions of the car that are intended to have work done on them during collisions and to absorb that energy in a way that's safe. It's time for a question. A 10-year-old child who is a good baseball pitcher can throw the baseball at 50 miles an hour as a fastball. That's about 80 kilometers per hour. But it takes a world-class professional pitcher to throw a fastball that travels 100 miles an hour or 160 kilometers an hour. Compare the kinetic energies in those two pitches. The faster moving baseball is carrying 4 times as much kinetic energy with it, even though it's only traveling twice as fast. That enormous increase in kinetic energy explains why it's so hard to throw a 100-mile-an-hour fastball and why only a few people have ever been able to do it. Moreover, they throw that ball in a shorter period of time than a person throws a 50-mile-an-hour fastball. So they're pouring their energy into it, that is, they're pouring 4 times as much energy into it in roughly half the time, which involves a much more rapid transfer of energy, that is, more power. Throwing a 100-mile-an-hour fastball requires something like 8 times as much mechanical power as throwing a 50-mile-an-hour fastball. Now let's look at the kinetic energy associated with the wheel's rotational motion. That kinetic energy is the work it takes to bring the motionless wheel up to its final angular velocity. The rotational story will be almost exactly the same as the translational story, but this time I'm going to do rotational work by exerting a torque on the wheel as it rotates through an angle. Well, as before, as with the translational story, I'm not going to do everything. I'm going to look instead at some important observations. And the first of those, there are 3 of them again. The first of those is that the direction of angular velocity doesn't matter, whether I spin it, from my perspective, clockwise or counterclockwise. This is rotation down. This is rotation up. It doesn't matter. I do the same work spinning it this way as spinning it this way. So, what matters is not angular velocity, the whole thing, but rather angular speed, the amount part of angular velocity. The direction part of angular velocity, not important, because once again, energy is about doing, not about moving, and direction doesn't matter. Second observation, this one is about rotational mass. It turns out that the kinetic energy associated with rotation in a wheel is proportional to the wheel's rotational mass. To show you that, I'm going to get my second wheel. So here we have second wheel, same as the first, but instead of moving them around separately, I'm going to sit this wheel on top of the first wheel. Well, if it took me 1 unit of work to get this guy spinning like that, it's going to take 2 units of work to get this stack, if I can do it, spinning like that. Basically, the amount of work I have to do rotationally to get one of these wheels spinning is proportional to its rotational mass. If I double the rotational mass, it takes twice as much work. 10 times the rotational mass, 10 times as much work. So, we know now that the kinetic energy in an object's rotational motion is proportional to its rotational mass. The third part, the tough one, put this guy away, is how the kinetic energy in the rotational motion of the wheel depends on angular speed. And once again, that kinetic energy is proportional to angular speed squared for the same reason. If I exert a steady torque on this wheel, it undergoes angular acceleration steadily, constant angular acceleration, and it spins faster and faster and faster. So its angular velocity is then proportional to how long I twist it, the amount of time over which I twist it. If I twist it twice as long, it ends up spinning at twice the angular velocity. But the work I do doesn't go up proportionally with time for exactly the same reason that we saw with translational motion. As I spin this little guy, I exert a torque on it, a constant torque, and it undergoes angular acceleration. It goes faster and faster. The work that I'm doing depends on the angle through which it rotates. It's the torque I exert times the angle through which it rotates. And as it picks up angular speed, it rotates farther and farther with each additional second. So I'm chasing it around in a circle. The first second it doesn't turn very far, and I do relatively little work on it. The second it turns farther, and I do more work on it. Third second farther still, and so on. I'm chasing it around the circle. So the energy, the work I have to do on it skyrockets, and so does its kinetic energy. The kinetic energy in a wheel's rotational motion turns out to be equal to 1/2 the wheel's rotational mass times the square of its angular speed. Fast spinning wheels can therefore carry enormous kinetic energies, even when they're rotating in place. The wheels on a moving vehicle, however, are translating and rotating at the same time. What about their kinetic energies? It turns out that those kinetic energies add up. When your bicycle is moving forward, each wheel has translational kinetic energy associated with the velocity of its center of mass, and rotational kinetic energy associated with its angular velocity about its center of mass. That double dose of kinetic energy distinguishes the wheels from the rest of the bicycle. Bicycle wheels carry more kinetic energy per kilogram than any other part of the bicycle. And since you have to provide that energy as work when you pedal the bicycle forward from rest, the wheels make your job more difficult. Similarly, the bicycle's brakes have to get rid of that extra energy when they slow the bicycle to a stop. So because of these effects, extra energy in, extra energy out in the wheels, those wheels are generally designed very carefully to reduce both their masses and their rotational masses. Replacing a solid rubber tire with an air-filled pneumatic one not only reduces the wheel's weight, so it's easier to lift and carry uphill, it also reduces the wheel's mass and rotational mass, and thus reduces the kinetic energy that the wheel carries as it moves.